close this. Okay. So we danced around some of chapter 6 already when we were talking about chapters 1, 2, and 3. Chapter 6 also has the sections that kind of go through what a solid, liquid, and gas are. So we already kind of covered that. So we're going to kind of just jump around in here. So you've already kind of covered those things, but you can go into more depth with them in this chapter. So the first topic we're going to talk about is the concept of kinetic molecular theory. Oftentimes, if you're looking at online resources or something like that, they call it KMT. But basically, this is kind of just observational things about gases that we have come to understand how gases behave. Some of these should, seem pretty obvious, right? Matter is made up of teeny particles. These particles, right, if we're talking about gas, are in constant motion. Therefore, they possess kinetic energy, right? The difference between kinetic energy and potential energy would be that kinetic energy is, energy in motion, and potential energy would be, the potential of energy falling, or energy in motion. So if I have a pen and I drop the pen, when it's up here, it has potential energy, and then when I drop it, it's into kinetic energy. So because the particles are always moving, right? Not just gas particles floating around the air, but even in your your desks and everything, those little molecules and atoms and the electrons in the atoms, everything's moving. It's just we can't observe that, but they're all moving. They possess energy as a result of repulsions and attractions to each other. So think about things we've talked about where we have like electron clouds and things like that. Think of your VSEPR theory, right? Electron repulsion theory, of how we get the shapes of our molecules and everything like that. We're going to talk a little bit more about our Lewis structures, right? And so what we have going on is this idea that the energy that they have, the potential energy, right? If like two particles are coming closer and closer together, there's going to be a potential energy of either of them coming really close together or them coming closer and being like, ugh. So there's a potential energy there based off their attraction or repulsion. Specifically when we're talking about gases, average particle speed, what we're talking about here is, right, gas particles, the best way we can kind of think of them would be like little kids in a bounce house. Little kids in a bounce house, that's their container. The bounce house is the container and the little kids are the gas molecules. And they're just bonging, bonk, 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 off the walls and ceiling into each other. And they just kind of never stop moving. That they are affected by temperature. So, if it's really, really hot, they're getting all amped up. And then as it gets colder, they start to move slower. So we actually have the speed of a gas affected by the temperature. And for any of you who have taken like a physics class, we also see this happen with sound. And that's, because matter is traveling, or sound waves are traveling through matter, which is going to affect it as well. And then particles will transfer energy from one to another during a collision, but no energy is lost. So what we're talking about is if you have two gas particles and they have some sort of, collision, right? Let's say one's a hydrogen and one's I don't know, what's something really big, a neon or something like that. And they go, right? When they hit into each other, right? One might absorb some of the energy of the other one in the transfer, right? It could be like a billiard ball where like this one hits into that one and then this one moves away, or they could do one of these. But in either way, the total system, right, that closed container didn't lose any energy. It just transferred from one molecule atom to the other. So we have a couple equations that we use to kind of define these energies that we're talking about. The one you will need to know, so this would be a good one for your notes so that you don't have to memorize it, would be kinetic energy is 1/2 the mass of whatever the particle is, multiplied by the velocity of it squared. So again, this is just a way to figure out kinetic energy. In terms of how we would be using this, homework problems would be a good place to see this, but basically we could tell you the type of atom it is, and then you would have to figure out the mass of it based off of your periodic table, because now you know how to do that, right? Of an individual mass of an atom, or we could give you the energy of it and the speed, and maybe you have to figure out which atom it is because you would have to figure out the mass, right? So just kind of a lot of playing around with, algebra of different ways to look at an equation. So a warm-up question, which of the following is not part of kinetic molecular theory? Molecules are in constant motion. Molecules attract and repel each other. Molecules move faster at lower temperatures, or molecules transfer energy during collisions. Hello. So if you want, you can send it in the chat, or you don't have to, or if you want, you can just kind of say it to yourself, or however you want to do it. It's fine by me. Just give you a second to read through them. What do you think it is? The correct answer for this one, which is not a part of kinetic molecular theory, would be number 3. Molecules move faster at lower temperatures. That is incorrect. Molecules move slower at lower temperatures. They move faster in hotter temperatures. So that was the answer to that one. Okay. So when we are calculating kinetic energies, I'm going to kind of breeze through this one. I will post an answer to this question, but because I give you guys the extra time, I don't want to spend it on doing a calculation. But again, let's go through the problem and just identify the pieces of it. Calculate the kinetic energy, the KE, of 2 particles with masses of 2 and 3 grams if they are both moving at a velocity of 15 centimeters per second. So in this case, you're going to have the kinetic energy of 2 different atoms. You're given the masses of both and the velocities of both. So it's a plug and chug of 1/2 times whatever mass we're dealing with times the velocity squared. All right. Gases, we have a lot of gas laws. Again, these are things that a lot of them make sense when you kind of walk through them in your head in terms of pressure, volume, temperature, that kind of thing, and how they relate to each other. But we're just going to kind of logic them out in our heads. So you will have questions where it's more of a qualitative thing, where it's like, if this doubles, what will happen to this? You know, and there's no real numbers involved. And it might have it, it might quarter it, it might double it as well. It depends on what it is. So we have Boyle's law, which relates pressure and volume. We have Charles' law relating volume and temperature. The combined gas law is a way to kind of, you will see this most often when we are dealing with things where it's like, okay, I have a piston or a canister filled with some sort of gas at this temperature. And then, it's put in an oven at this temperature. What is, the final pressure? And so in a case like that, you would have had all of this information already. And because it's in a closed system, the volume would remain the same. You were told the temperature, changed, so that maybe it was in an oven at 350 or something like that. And so you would just be solving for this. So it's a lot of algebra rearrangements. The other big one that we will be dealing with is the ideal gas law. The ideal gas law will come into play in terms of taking gas laws and applying things like limiting reactants. So chapter 5, we started talking about 4 and 5, right? We started talking about limiting reactants and like the thing that limits the amount of product that can be produced. This ideal gas law will help us kind of do that similar kind of system with gases, because right here, this little n represents moles of whatever gas we're talking about. And so oftentimes if we're given 2 amounts, we can figure out the pressures, or if we're given all this information and we were like, oh, this kind of looks like it's a limiting reactant problem, what you're going to be given is pressure, volume, and temperature. R is a constant. You'll see it in a second. I would write that down in your notes. And then you're going to have to solve for the moles. And then once you have the moles of the 2 substances, then you're doing like a classic limiting reactant problem. So again, in terms of your gas laws, I would encourage you to write these down in your notes so that you have them as a reference for yourselves. Since we are in an 8-week class, you want to make this as easy on yourself as possible in other places. So P and V respond to pressure and volume. Okay, and K is just whatever, the constant's going to end up being. V and T would be volume and temperature. And then the combined gas law is pressure, volume, and temperature. So we're going to see some examples of these things. So like I said, the combined gas law, the way we're most likely going to see questions and problems with it will be like you are going to be given an initial or perhaps a final set of conditions and then some information about the other end of it. So maybe you're told after, some heating, final temperature was this, the volume of the closed container was this, and the pressure was this. If the initial temperature was, room temperature, what was the initial pressure or something like that. So the little I's refer to initial, the little F's refer to final. Okay, so we can go through kind of one of these gas law problems together and see where we're at. So a gas sample has a volume of 250 liters. Excuse me. So whenever you're doing a gas law problem or any problem really where it's a word problem and there's not a whole lot of like obvious numbers to them, is start kind of picking out the pieces and being like, volume 250 liters. So I'm going to write down V equals 2.5 liters. So the V equals 2.5 liters. The temperature, temperature is 30 degrees Celsius and the pressure is 180 atmospheres. Okay, so I have a volume, a temperature, and a pressure. I have a V, a T, and a P. Okay. What volume in liters will the sample have if the pressure is increased to 3 atmospheres and the temperature is increased to 100 degrees Celsius? So a couple important things that we need to talk about here. As you'll read in your textbook, when we have gas laws of any kind, excuse me, one sec. When we have gas laws of any kind, what we're going to have to talk about is kind of remembering in our head, if I'm given a temperature not in Kelvin, I'm going to have to put it in Kelvin. The first reason we need to do this is because temperatures in Celsius and in Fahrenheit, but we're in a science class, so Celsius, they can be negative. So it's not out of the norm. Well, in San Diego it is, but it's not out of the norm even for like temperatures that humans see regularly. If it's winter in Michigan, it very easily can get below 0 degrees Celsius. It can get below freezing. And those would be negative numbers. So when we start thinking about things in terms of using a negative number in something like this, you would end up possibly with like a negative volume, which wouldn't make any sense. Like what the hell would a negative volume be? So just as a caveat of math, that would happen. So what we do is we use Kelvin, and Kelvin, there are no negative numbers. The absolute 0, like the coldest it could possibly be, where like atoms and electrons freeze, and would be that cold, would be 0 Kelvin. So we're not going to experience 0 Kelvin in any situation that we're dealing with in these calculations. So we'll always have a positive integer. So like we talked about, identify which are the initial and which are the final conditions. So we have this telling us here a volume of 2.5 liters. This would be my V initial. A temperature of 30 degrees Celsius. Well, it needs to be converted into Kelvin, but this would be my initial temperature. And a pressure of 180 atmospheres. This would be my initial pressure. And then we're told what volume in liters will the sample have if the pressure is increased to 3 atmospheres. So this is our final pressure, and the temperature is increased to 100 degrees Celsius. In Kelvin, this would be our final temperature. So in that case, you have this, you have this, you have this, you have this guy, and you are solving for this one. So it is an algebra plug and chug situation. So here I've kind of written it all out for you in terms of how you would kind of solve for it. A lot of students like kind of like an initial column and a final column, where you can kind of easily identify what are the pieces you need. Here I've just rewritten the combined gas law for solving for volume. One thing I like to warn students when you're doing things on your calculator, students have a tendency to try and put this entire thing in one go in their calculator. So there's a ton of parentheses and things will inevitably get screwed up. I would encourage you to maybe solve for this number and solve for this number and then divide them at the end. In your calculator, at least, I know it's an extra step, but you don't have those 30,000 parentheses where you're going to have an oopsie somewhere. And then either you get the wrong number or there's, a calculator error or something along the way. So when you do that, it would look something like this in terms of putting all those numbers in there, and you should get something around 1.85 liters. So again, this one's relatively simple because we have our significant figures. Everything here had 3 significant figures, but this is all multiplication and division. So it would be based off of whatever had the least number of significant figures. Remember, both of these zeros and this 0 and this 0 are all significant because they come after the decimal place and there are non-zero numbers before them. So I'm gonna let you guys try it out on your own one, and tomorrow I will post into the resources section the worked out math for this one. One of the other crazy things that happens with gases that we've noticed has to deal with Avogadro's law for gases. And as you can imagine, it has to deal with moles because it's Avogadro. And the long and short of it is that we have noticed at standard temperature and pressure, also called STP, which would be 0 degrees Celsius and 1 atmosphere. That's standard temperature and pressure. 1 mole of any gas will be 22.4 liters. It's kind of a weird caveat of nature that the gases will be occupy 22.4 liters. So this is important to know simply because a lot of times what ends up happening is on a homework question or on a test or something like that, you have some sort of gas law equation that you are working on, and it tells you, there are, X number of moles of sodium hypochlorite gas, and it's at standard temperature and pressure. And it'll say, how much does it weigh or something like that. And what you're able to do is you go, God, I don't have enough information for this. But you can use Avogadro's law, because if it's at standard temperature and pressure, you have the equivalent, the equality of 1 mole equals 22.4 liters. And that's often a way to help you get from a known volume to a known number of moles, which then can help you get to a molar, to a mass of, your sample, because if you know what the sample is, how many moles of it you have, you can use the molar mass to get that. Like we said, the last gas law that you'll need to kind of work on, again, this is one of those ones where I would encourage you to write it down, would be the ideal gas law, PV equals nRT, PIV-NERT, sometimes it's called. But basically, this combines all the different gas laws into like one mathematically sound expression. Oops, sorry, my computer's slipping off its stand. Oh my goodness. And that would have been really bad. And so what we have happening here is P and V, right? Pressure and volume. T is temperature in Kelvin. N would be the number of moles in the sample. And then we have this universal gas constant, which is R. So this number will always be the same. Now, the hint and trick here, in your homework, you might see different R's in the reference tables, and it's based off of these units here. Now, this is the one that we're pretty much always going to go with because we're going to convert any of our other portions of it into these units. So you can see in the universal gas constant, these are all the units associated with R. So it has liters, it has atmospheres, it has moles, it has kelvins, which are the same as what's used in pressure, volume, and temperature and moles. So it's a unitless number that we would end up using. So it's kind of like a fudge factor. If let's say your volume was in milliliters, then you're going to have a different R here, or just convert your volume into liters, and then you would be able to use it. There are plenty of reference charts which have like every combination of the R values possible. I find those tedious and time consuming to use as a reference. I find it much quicker to just convert everything into liters, atmospheres, moles, and Kelvin, and just use one universal gas constant. That's just me. You're going to be showing your work, so I don't really care which way you go. I just find that it's quicker to do it that way. So let's look at how a problem would look if we were using the ideal gas constant, or excuse me, the ideal gas law. We have 2.5 moles of a sample of a gas that is combined to 6.17 liters in a tank at a temperature of 28 degrees Celsius. And we want to know, what is the pressure in atmospheres of this gas? So this is going to be kind of a setup of a long dimensional analysis, right? We could do it that way, or we could literally plug and chug into our ideal gas law. And again, it's really important when you're doing your work, if you're putting units in with your work, it's kind of hard to screw it up. The units always kind of make sure that you are on the right track. I like to say that it prevents those shit moments when you're doing your math. If you put in the units and all the units cancel out and the only thing you're left with is the thing that you wanted, then you did it right. So the thing we want here is gas and atmospheres. So when I plug and chug everything in, my moles of my sample, my R, which we know is this guy, my temperature in Kelvin, and my volume in liters. Moles cancel out with moles. Liters cancel out with liters. Now remember, the liters down here is in the denominator, and this is in the numerator of a denominator. If you need to go review some math with that, this liter and this liter would cancel out. Kelvins is in the denominator here, even though it's still in the numerator overall, but these two can cancel out. So the only unit that doesn't cancel out is atmospheres. Hey, that's what I was asked about. So I must have set this up right. So units will always help guide you. Students oftentimes forget to add them, and it can, sometimes you have an oopsies and a brain fart, and you may have been on the right track and you may have flipped something around, and if you're not checking your units, you may have not caught yourself doing that. So again, here's another try it on your own. I will post this to Canvas. Okay, the last thing with the ideal gas law, one of the ways we can do this is to help us determine molecular weights of gaseous substances. Why we would care to do this is maybe one of the ways this is applicable in like a real world situation is in Defense Department and things like that. If there is some sort of what we believe to be a chemical gas attack, unfortunately, these things do happen. And we kind of wonder, perhaps it was one of the big no-nos that isn't allowed to be used and is like a qualifiable war crime. What we can do is, if we are able to use information about the gas and the moles of it, we can actually determine the molecular weight of that gas. And we know, sarin gas and things like that, we know their molecular weight. So if a sample was able to be taken of the suspected, chemical used in the attack, we would be able to reference it against, known molecular weights of, very toxic and noxious gases to get a better idea of perhaps what we're up against. This could also be done if a patient comes into like an emergency room situation and it's maybe not presenting as like classic carbon monoxide poisoning or something like that, and we believe it is a gaseous substance that they've been poisoned with. Oftentimes a lab will basically take this approach to figure out what the probable gas is, if that's what we think is happening. And then from there, obviously, once we know what we're up against, we would be able to treat accordingly. So that's, a little bit of the why would we care about this situation. So when we're going through this, right, basically what we're able to do is kind of manipulate that PV equals nRT. And we know that moles would be the mass divided by the molecular weight. That's what moles is, right? So grams divided by molecular weight tells us moles. So all we're going to do in PV equals nRT is replace N with this equation right here. And so it would be PV equals M for grams, RT over the molecular weight of whatever the substance is. Now, if it's an unknown substance, this is the thing you're solving for. So you would need to know the pressure, the volume, the mass of the sample, and the temperature at which the sample was taken to make that work. So, right, again, this is one of those things where we would apply this, right? 4 grams of a sample is found to exert a pressure of 1.7 atmospheres when combined in a 3.6 liter container at a temperature, basic 27 degrees Celsius is basically room temperature, was the molecular weight of the gas in grams per mole, right? Grams per mole. So when we're looking at our units, we're solving for this part right here, grams per mole, M over MW. Right here. The molecular weight is equal to the sample of the mass in grams, right, divided by the molar weight. So we can take PV equals nRT and import this one into it. And since the sample of the mass is known, we're told we have 4 grams of it, right? So we can already put the M here. All we have to do is solve for the molecular weight then. So we'd have a setup similar to this, where we know that we have the 1.7 atmospheres, 3.6 liters, R is our constant, and then 27 degrees Celsius converts to 300 degrees Kelvin. We do a quick check of our units. Atmospheres would cancel out, liters and liters would cancel out, Kelvin and Kelvin would cancel out, and so my number of moles is all I have left is 0.25 moles. And I already knew from the problem that I had 4 grams. So it's 4 grams for every 0.25 moles. And then you would be able to calculate the molar mass based off of that. Now, you all have been doing a lot of work. 16.0 grams per mole. What gas, that's really important for life, weighs about 16 grams per mole? I'll give you a hint. It's diatomic. What do we think? Maybe oxygen? So things like that will be problems that you will see in your homework, applications of this kind of thing in your homework, and test problems will come up like that. So, all right. How'd we do? That was the end of chapter 6. All right, if we're good, we're gonna move on to chapter 7. Let me bring up chapter 7. Bear with me one moment, please. Click, go. All right, take a minute, get yourself set up. If you do have questions, you can put it in the chat or just use the raised hand and we can go from there. So chapter 7, we are now talking solutions. Solutions will be kind of its own language a little bit. We're going to learn some different terminology in terms of what we consider a solution. Again, this might be something you're not necessarily familiar with. A lot of people are comfortable with the idea of a solution being like salt dissolved in water, like table salt dissolved in water. But we can also think of solutions as an alloy. You know, 2 metals mixed together, or perhaps a liquid and a gas. Real quick, chapter 6, as it says in the the module, the whole chapter we did already in chapter 1, 2, 3. In that first week, we talked about the differences between solids, liquids, and gases. So you are still responsible for that portion as well. We just didn't cover it today because it made more sense to talk about it last week. So I was asked if we need to know all of chapter 6 or just what we talked about in the slides. So again, when you look on the suggested reading for the week, it tells you which sections you need to go read. Those are the sections you're responsible for. And then these are just the highlights of like the big things. And then hopefully you're able to put it all together. But if you have questions, email me. Like I said, I try and open up the first part of class to give you time to ask questions and things like that. So we're going to talk about a couple different ways we can consider something a solution. There are three parts to a solution. There's the solute, the solvent, and the solute and solvent together are called a solution. So we're going to talk about what is a solute, what is a solvent. So first of all, solutions, as we are going to be talking about them, will be homogeneous mixtures, right? So remember back to all the way back, right? So long ago to last week, when we talked about what a homogeneous mixture was, right? A homogeneous mixture is something where we can't distinguish the parts of it, right? So if I have, again, the really good example is table salt dissolved in water. If I have salt water, I can't sit there and go, oh yes, here's an NaCl and here is, you know, an H2O. And as we know, NaCl actually wouldn't be NaCl in water, right? Because it's an ionic compound, which would dissociate 100%. So we would actually have Na plus Cl minus in there, but that's not what we're worrying about right now. They can be colored or transparent. It's very important. A lot of students struggle with this. There is a difference between clear and colorless. Clear is something we can see through, but it could still be colored. We could have a clear yellow solution or a clear red solution, right? Urine, God willing, is yellow, pale yellow, and clear. If it's not, we have a whole other, you know, line of things we need to test. But typically, urine would be clear, which means transparent or see-through. Colored would just be a tint to whatever color we're dealing with. So sometimes vernacularly wise, when we're describing things, we say clear where we mean colorless, and things like that. Particles in liquid solutions are too small to reflect light, and they're in constant motion. So if we actually have a solution, it's constantly, just like everything else, kinetic molecular theory, they're moving and shaking in there. They do not settle under the influence of gravity because there's a lot of those intermolecular forces going on. So that plays an effect on it. And the physical state of a solution is the same as the physical state of the solvent. So if the solvent is liquid, then the solution is liquid. If the solvent is solid, then the solution is solid. And it's odd to think of a solid as a solution, but in terms of defining it by its parts, it could be. So when we're talking about what are the parts of a solution, we're talking about the solvent and the solute. Those two things combined together make the solution. The solvent is typically, if we're talking in technical terms, when it's not obvious like a liquid and a solid situation, in technical terms, the solvent is the thing that we have a larger amount of in moles. So this is when I'm talking about things like a solution of metals, like we have in an alloy. Whatever we have the most of would be the solvent. The solute would be the thing we have less of. Oftentimes what you may be most comfortable with in terms of solvent and solute would be, you know, a solid being dissolved into a, a liquid. We also see gases in liquids. So obviously in nature, fish in a pond in the ocean or anything like that, they don't breathe air, but they still breathe oxygen, and the oxygen flows over their gills, and that's how they get oxygen, and they're getting oxygen from the water. And this is why it's very, very crucial. We'll find out that the solubility of gases in water is the exact opposite of the solubility of solids in water. So we've hit summer and it's hot as balls out. So we are now on to our iced coffee phase of existence. And when it's iced coffee season, that means that you get your iced coffee, you pour in your sugar, and you get diabetes explosion at the bottom, right? It doesn't dissolve as well because you have a cold solvent, or excuse me, you have a cold solvent, and the solute, the sugar, does not dissolve in it very well. But we know that when it's cold season for us in San Diego, that means that it's hot coffee season, and it's very easy to pour in your sugar and sweeten your coffee. Gases are the exact opposite. More oxygen is soluble in cold water than it is in hot water. And it makes sense when you think about it. We just talked about gases, kinetic molecular theory. What happens to gases when it gets hot? Do they move faster or slower? They move faster when it's hot, right? So if the water is hotter, that means the gas particles are moving more quickly, which means they can escape out of the water more readily and join the atmosphere, which means in ecological standpoint, we're talking about as oceans, lake beds, things like this, the temperature rises, we are getting less and less water filled with oxygen. And this is how we get dead zones in the water. So that is really one of the huge concerns when we talk about rising water temperatures. It has to do with its ability to support life. Okay, so moving on. A solution is when we have one or more. We could have multiple solvents or solutes in our solvent. We could have sugar and salt and, I don't know, onion powder. We could be making a soup, a really gross soup into our solution. So we could have multiple solutes in one solvent, and that could be our solution. So again, these are just some examples of different solute, solvent, solution mixtures, gases, liquid, solids. Again, we're really usually fine with the liquids. The gases and solids are the ones where we kind of get caught up. So solubility, or how likely is it that the solute will mix into the solvent? How likely is it that we're going to get a solution? Now, solubility is kind of a sliding scale. Like we just talked about with our iced coffee conundrum. If we're talking about sugar dissolving in water, it's really temperature dependent, right? Like if I have a cup of sugar and I mix it into, a quarter cup of water, if the water is really hot, I can make that whole cup of sugar go into that little tiny quarter cup of water. But if the water is ice cold, it's not going to do anything. So solubility is really going to be temperature dependent, and we kind of have a sliding scale for that. A soluble substance would be something that dissolves or dissociates to a significant extent. So pretty much it all goes away in the solvent. Insoluble would be it does not do that. And then immiscible are liquids that are insoluble in each other. So immiscible would be oil and water is a really good example of an immiscible liquids. Gases and their solubility, we already talked about this, but it's inversely proportional. Inversely means as one goes up, the other goes down. So in this case, as temperature goes up, the solubility of the gas goes down, and they're directly proportional to each other. So again, what we'll see if you have like a chart of solubilities as like a reference or something like that, the general unit that we use for it is grams of our solute per 100 grams of water. So when you see something like 0.6, right, for sodium bicarbonate, 6.9, this would be 6.9 grams of sodium bicarbonate for every 100 grams of water. That would be soluble. Then there are things where we could have sodium iodide, 144.6 grams, or something like ethyl alcohol. This is what you probably need to get through our class with. This is booze, ethyl alcohol. It's infinitely at certain, when they're soluble in all proportions. So we have things that are infinitely soluble. We have things that are hardly soluble at all. For example, calcium carbonate. So it really depends on the substance. And again, temperature will play a role here. So these are examples at 0 degrees Celsius. So you can imagine how big and thick and crazy reference books for solubility are if they're at different temperatures and different solubilities and things like that. So oftentimes the way solubilities are expressed are charts like this, a solubility chart. And what this would be is we have temperatures along our x-axis, and we have solubilities in grams of solute per 100 grams of water on our y-axis. And this allows us to represent a lot of data in a very compact way. So we have different lines representing different materials. And as you can see, for example, something like a gas, we can see that at a colder temperature, we have a higher amount of solubility. And as the temperature begins to warm up, we get significantly less solubility. You can see for something like a solid that at cold temperatures, we have a very low solubility, and at high temperatures, we have a very high solubility. So here I just gave you some examples of different questions you could give yourself a try to answer them. So I'll go through the first one, and I have down here, you know, the answers to them, so you can check it out. But at 45 degrees Celsius, how many grams of KBr will be soluble in 100 grams of water? So the way I would have to look at this is go over and be like, okay, 45 degrees Celsius, I'm going to come straight up to KBr. And I'm like, that puts me about here on my line. And then I look over and I'm going to say, right, again, this is sig figs. We're reporting it, looking at it. I'm going to say 73 grams. Now, obviously, in terms of a question like this, there's a lot of right answers when you're reading a chart. But if you said 83 grams, you would definitely be wrong. And if you said 60 or 58 grams, you would also be wrong, right? Like there's no way, if it's falling somewhere between 60 and 80. So you would have a breadth of correct possible things there. What about 300 grams of water at 45 degrees Celsius? So now we're saying for my KBr, if I had 300 grams of water at 45 degrees Celsius, how much could I have? Well, we know for 100 grams of water, we'll call it the 73 grams, right? If we had 100 grams of water, you could say it was 73 grams. So if I have 300 grams of water, it's just going to be 3 times that amount. What is the minimum temperature? 100 grams of water to dissolve 200 grams of sucrose. So for this, we're going to look at our sucrose line right here. And we're saying, what is the minimum temperature required to dissolve 100 grams of water, of 100 grams of water to dissolve 200 grams of sucrose. So we know that this line here is in terms of 100 grams of water. So what we're looking at is, what is the lowest temperature at which 200 grams of the solute could go? So basically, we're just going to take the line over to where we think it's going to be. And this is a lot easier to do when you print out these things and you can like hold a piece of paper up to them or whatever. And so like we said, I don't know, 26 degrees Celsius, it looks like to me. But again, if you had said 17 or 35, you would be way off. All right. So degrees of saturation. Like we said, that these solutions are kind of in a spectrum, right? There's a wide breadth that we can look at in terms of our saturations. And when we're adding, a solute to a solution, a saturated solution would be the maximum amount of solute that we can get into this, the solvent while it's still stable at a certain set temperature and pressure. So for example, if I have my cup of sugar and water, it may be at room temperature, a saturated solution. Like I keep adding sugar until I can't get any more sugar to dissolve in it at room temperature. But I know that if I heat it up, I'm going to have a new set of conditions and it would actually no longer be saturated. I could get more into it. A supersaturated solution is an unstable solution that contains more solute than it really should be able to. And these things often are done by heating up a solution and getting it saturated and then very slowly cooling it while it's stable. And then the solution, the solute will stay in solution, but even the slightest disturbance to the solution could cause it to what we say precipitate out or fall out of solution. This could be something as simple as flicking the beaker or scratching the inside of the beaker. That could be enough disturbance to have it precipitate out. So here, interpreting degrees of saturation and solubility, you can go through and roughly approximately go through and tell me what the solubilities are of each of these compounds. I will post again to Canvas the answers to those ones as well. Now for this slide here, this will be the last slide I'm going to talk about for today. And then you'll have to go through the rest. There are some really great videos on this. This image here in the resources slide is an animation of this, and it makes a lot more sense when you watch the animation of it. So I really encourage you to do that. It's called The Hydration of a Salt video. It basically, like, the thumbnail of it looks exactly like this. So go find that one. That's a really good video to watch, like in motion kind of thing. But obviously one of the most popular solvents in the world would be water. And that's partially because water is a very polar molecule. When we look at water, we can see that the bonds between the hydrogen and the oxygens, right? Oxygen is more electronegative, hydrogen is less electronegative, so the electrons are hanging out at this end of the bond. And because of that, we get a slightly negative, slightly positive kind of thing going on here. Remember, these aren't real polar bonds, right? It's not, excuse me, it's not an ionic bond. It's not a positive and a negative. They're still sharing them, but it's a slightly positive, slightly negative situation. And because of that, we also see that it's got this bent shape, right? And when we have this bent shape, that means I could take like a knife and cut down this side of the molecule, and I'd have a slightly negative head and a slightly positive tail. And because of that, the overall molecule is polar, right? That there's a positive side to the molecule and a negative side. And that allows it to really facilitate dissolving things and dissociating things. So up until now, you may have been comfortable with the idea of using the words dissolve and dissociate interchangeably, but they're really not. They mean two different things. And so we're going to talk about that a little bit. But in either case, let's say here, this green and silver thing is an NaCl molecule, like a square of table salt, where these greens are the chlorines and the silvers are the sodiums. What water will do is position itself where either the positive tail or the negative head is surrounding different ions of the molecule. In this case, the water will start to surround a negative chlorine by posing the positive hydrogens around it, and it will cluster around it, and it will say, hey, chlorine, you want to come hang out with us? We're way cooler than the rest of the salt molecule. And then the chlorine goes, okay. And so the chlorine pieces out with the waters, and so the waters surround it and they take it away. The same thing happens with the sodiums, but now it's the negative side of it that does it, and it looks like this. So there's a really nice video that you get to kind of watch it, like surround, cluster, and take it away, so that you can understand physically, watching it's really nice to do. This will cause a salt or any ionic compound to dissociate. And what we mean by dissociate is that we are actually taking this molecule apart. It no longer would exist as NaCl, the ionic compound. It's going to be Na, the cation, and Cl, the anion, like you see here. So when salt dissolves in water, what it's really doing is dissociating water. It's no longer salt. It's no longer NaCl. It's existing like this. This guy, when it's fully, broken up, only exists like this, as these ions. And that's where we're going to end it there. Sorry, class has ended. I will hang out for a bit to answer some questions. Please go look at the resources. Tomorrow I will have posted the try it on your own and any questions you might have with that. The resources will be a really good area for you folks with that. But you can head out if you're good and you don't have any questions. Otherwise, stay on. I will put everyone back in the waiting room, and I will take each of you in at a time, and we can go from there. Are there any general questions or things that you would like to ask as a whole before you leave? You can raise your hand. I'll go through those. If you have a personal or private question that you want to talk about, just hang on and I'll throw you everybody in the waiting room and go through those privately. So any general questions for anybody? Okay. Like I said, let me know if you have questions. I will throw everybody into the waiting room, and then you can either just leave out now or go ahead and I will send everybody in as one at a time. So let me just see how I do this again. Sorry, bear with me 1 second. Okay. Ooh, okay. No? Okay.
I'm good. I didn't leave fast enough. You're
No
faster.
worries. It's totally fine. All right. Have a good afternoon.
Thank you. You too. Bye.
Bye.
Hi, Dr. S.
Hi.